When you think about shaping metal, you probably picture brute force, right? Fire, hammers. But in the world of high-tech manufacturing, it's way more of a delicate science. One tiny mistake, one variable off by a fraction, and the whole thing can fail. Today, we're going to crack the code on how to forge perfection.
And really, that's the big question, isn't it? In a world that demands millions of identical parts, where you absolutely can't afford a single flaw, how do you guarantee a perfect product every single time? Well, the answer lies in a pretty revolutionary process and a secret formula we're about to uncover.
All right, let's dive in. Our story really starts at the cutting edge of manufacturing. We're talking about a place where metal is basically sculpted with the precision of a surgeon.
So here's the tech we're talking about: incremental sheet metal forming, or ISMF for short. Now, forget about those massive, super expensive metal molds. With ISMF, you use a computer-controlled tool that, well, it pretty much draws a 3D part into existence right from a flat sheet of metal. It's incredibly flexible, it's precise, and it's what lets us create those complex, lightweight parts that are making our cars safer and our planes more efficient.
And this is our material of choice for this investigation: SS304 stainless steel. With its special mix of chromium and nickel, it's tough, it doesn't rust, and you can shape it into all sorts of complicated forms. It's basically the go-to workhorse for the modern car industry. But even the strongest materials have a breaking point.
And this is where the plot thickens. Because this futuristic process, it has a dark side. It can create these tiny, hidden imperfections that can compromise, well, pretty much everything.
So the mission is simple on the surface: get a perfectly smooth finish while keeping the metal as strong as possible. But there are two main enemies standing in the way. First, you've got surface roughness, a flawed finish that just screams low quality. And then you have the really dangerous one: catastrophic thinning. That's where the metal gets stretched so far that it becomes dangerously weak.
So what do? Well, a team of researchers decided to go on a hunt, a scientific investigation to find the secret formula that could defeat both of these enemies and finally unlock perfection.
Now, every good investigation needs a map. For them, it was something called the Behnken design. It's a really powerful statistical method that lets you test a whole bunch of variables at the same time and, crucially, see how they all interact with each other. It's really the only way to find your way through this maze of possibilities.
And these are our three main suspects, the variables that could be causing all the trouble. First up is the feed rate, which is just how fast the tool is moving across the metal. Second, the tool speed, or how fast it's spinning. And finally, incremental depth. This is how deep the tool presses into the metal on each pass. The secret, the perfect formula, has to be hidden in some combination of these three.
Okay, so to sift through all the data, they needed a decoder. In this case, it's an algorithm called TOPSIS. Just think of it like a super smart logic engine. It takes all the results from the experiments, figures out what the absolute best and worst case scenarios are, and then calculates how close each test run got to that perfect outcome. Its whole job is to find that one single, ideal solution in all the noise.
So the map was drawn, the decoder was ready, and the experiments started. Now it was just a matter of following the clues, because the data doesn't lie. And bam, here's the first major clue. When they looked at surface roughness, the results were just wow. They used a tool called ANOVA, which basically tells you which suspect is having the biggest effect. The higher the F value, the more influence it has. And just look at the bar for incremental depth. It has an F value of 960. It completely dwarfs the others. We have found our prime suspect.
So what does that actually mean in plain English? It means that pushing the tool too deep into the metal is the #1 cause of a rough, flawed surface. It's kind of like trying to do fine carving with a massive, dulled chisel. You're just being too aggressive, and you're leaving a mess behind. This was their biggest lead by far.
But hold on. What about our other enemy, the thinning? Well, this is where it gets tricky. The clues here are a little more complicated. Now all of a sudden, the tool's rotational speed is a huge factor, and so is incremental depth again. But the feed rate? It barely matters. This complicates the whole case, because the perfect formula has to solve both problems, not just one.
So all the clues were on the table. All the data was fed into the TOPSIS decoder, and after processing every variable, every interaction, every single outcome, the code was cracked. The combination was finally unlocked.
So, you want to know the secret formula? Okay, the first part of the code, the perfect feed rate, is 1,000 millimeters per minute. A slow, steady, controlled advance.
The second number in the combination, that perfect rotation speed for the tool, turns out to be
550 revolutions per minute, right in that sweet spot, the perfect middle ground.
And finally, the most critical number of them all, the one that had the biggest impact on our prime suspect, that's surface roughness.
0.2 millimeters, a very shallow, very precise indentation.
And there you have it. That specific combination, 1,000, 550, and 0.2, that's the magic formula. It's the one single setting that keeps the surface smooth and stops the metal from thinning out. It takes out both enemies at the same time.
And look, they didn't just take the computer's word for it. They ran confirmation experiments, and the results were dead on. This isn't just a theory anymore. It's a verified, repeatable blueprint for forging perfection with SS304 stainless steel.
So we've cracked the code for one incredibly important material. But that just leaves you with a bigger thought, right? This entire method, this methodical hunt for the perfect formula, can be used for anything. Imagine lighter and stronger jet parts, or medical implants that last a lifetime. What other advanced materials are out there, just waiting for someone to come along and unlock their secret code?